Okay, last and finally, problem 5. We have a cave rescue team lifting an injured spelunker directly upward and out of a sinkhole with a motor-driven cable. Performed in 3 stages. Each one takes 10 meters. First, he goes from stationary to 5 meters per second. Then he's listed at 5 meters per second for 10 more meters. And then finally, over the last 10 meters, he's decelerated to 0 speed. How much work is done on the 81 kilogram rescuee by the force lifting him during each stage? So here what I've got is a little diagram. These are our stages, 1, 2, and 3. His mass is 86 kilograms. And so he starts here. After he's gone up 10 meters, so I'm marking off 10 meters here, he's got a velocity of 5 meters per second. After the next 10 meters, still 5 meters per second. After the third 10 meters, 0. So let's find his kinetic energy at each of these. Kinetic energy here is 0. Kinetic energy here is going to be 1/2 mv squared, which is going to be what? 43. 1/2 times 86 is 43 times 25. So let me just pull out the calculator. So 0.5 times 86 times 5 is 1,075 joules. Okay, great. 1,075 joules. His kinetic energy at this third point here, or really this is the second point, I'm actually going backwards. But kinetic energy here will be the same because it's the same speed, right? 1,075 joules. And then finally here, kinetic energy of 0. Okay, so now we've got that. Now we want to know the work done on this guy by the rope for each stage. Now, what's doing work on him? Well, first of all, the rope is doing some work. So the rope is doing some work, and gravity is also doing some work. So let's set up our work kinetic energy equation, which is work is the change in kinetic energy. And then we break the work down, and we say, and I'm just going to switch to a different color because I'm feeling, what's the word I used? Oh, saucy. I'm feeling saucy today, yes. All right. So it's the work done by gravity plus the work done by the rope. Okay, so that's these two getting broken up. And then that equals change in kinetic energy. Okay, so I'm just breaking this work up into 2 pieces and saying that equals change in kinetic energy. Okay, so let's go with purple now. It's a nice combination of red and blue. Okay, so what's the change in kinetic energy through this first stage? Well, it's plus 1,075 joules. Okay, I'm just going to leave plus 1,075. What's the work done by gravity on him? Well, he's going up 10 meters, right? So, and gravity is pulling down, right? mg is the force pulling down on him. So he's moving up. Remember, he's moving up through all these stages, but gravity is pulling him down. So gravity actually does negative work on him. So negative mg delta h. So negative mg times the height he goes through, plus, of course, the work from the rope. So W from the rope equals, actually, no, I'm going to leave this symbolic as delta EK for a moment. I'm going to take it back, and I'll show you why. Work for the rope, work done by the rope, is negative mg delta H plus change in kinetic energy. Okay? So for that first stage, okay, work done by the rope is negative mg delta H. So negative, and let's see, 86 times 9.8 times 10 meters. Okay, plus change in kinetic energy. So work done by the rope is going to be 86 times 9.8 times 10. So let's see. 86 times 9. Come on. There we go. 86 times 9.8 times 9.81, just to be safe, times 10. 8437 joules. Okay. Equals Let's see. Oh, okay. This should actually be plus because I had a negative with the W rope and I moved to the other side, so it should be positive. My bad. So what do we have? 8437. Okay, is positive 8437 joules plus change of kinetic energy. And for number one, so forget this was for number one. Now, really for number one, and I'll show you why I keep regeneralizing this, but okay, is 8437 plus his change of kinetic energy is 1035. Okay, so what is that? 8437 plus 1035 is 9472. Okay, equals 9472. Now here's the thing. That's for stage one. That's all great. Okay. What about stage two? Well, for stage two, he's going up another 10 meters, but there's no change in kinetic energy because he starts with, 1075 joules of kinetic energy here and ends with 1075 joules. So change of kinetic energy here is 0, which means but he still goes up 10 meters. So this is still the same equation actually, except delta EK equals 0. So that's why I left this general, because for stage 2 we can use this equation, but instead of having delta EK be 1075, because we were going from here to here before, now delta EK is simply 0. So for 2, work done by the rope should just equal the 8437, with this part being 0 instead. So 8437 joules. And then for part 3, he's going up, and it's 8437 joules done for gravity, but then he actually loses 10,000. Oh, I made a mistake. I did 75 instead of 35. My mistake. Okay, so this should be a 75, which means this should be a, so we added 40 here, so this should be a 9512. Okay, good to catch that. This is still all right. And then here we're doing 84. For part 3, we're saying, well, he's going up, but he's losing kinetic energy now, so the rope doesn't have to do as much work. So that's going to be 8437. W rope for number 3 is 8437 minus 1075. So let's see how well that works. 8437 minus 1075 gives us 7362 joules. Okay, so now the moment of truth. Pull up our assignment previewer. The middle one was 8437, and the first one was 9512. 9512, and then the last one was 7362. 7362, and so submit that for testing. Oh, but you know what? I got it all wrong because this is in kilojoules. The space here says kilojoules, so that's something you got to watch out for on these weather signs. They are sneaky. So I'm just going to turn these all into kilojoules. And oh my gosh, I'm still wrong. So let's see. What could I have done wrong? Well, oh, it's 81 kilograms, not 86. Don't I feel like a dumbass? So, oh boy, nuts. So let's see if I can at least fix my part B, right? So instead of 86 times 9.8 times 10, it should be 81 times 9.8 times 10. Okay, so 81 times 9.8 times 10. That's so 7938 joules for the middle one. Let's hope 7938, but we've got to convert it to kilojoules. So it should actually be 7.938. And if I submit, that is correct. So the other two are also going to be correct. I don't really have time to. Well, I guess I do. I could. So, and then the kinetic energy is going to be, oh god, the kinetic energy is going to be different too. So let's see if I can do this. So it's 89. Okay, so for the way up, or the first stage, 0.5 times 81 times 5 squared. So that's the total work done for stage 1 is 8951. So I'll just put in 8.95. 8.95. Fine. And then for the other stage, somebody's emailing me. Okay. And 6925, so 6.92525, and let's just see if these come out right. And they do, saved. So something to think about here is you had to do the most work during this first stage, and then less work here, and then less work here. If you think about why, think about if you're trying to pull something up. So at the beginning, it's sitting at the bottom. You have to give it sort of an extra jerk, an extra sharp tug to get it moving in the first place. But then once it's coming up, it's a little easier. And it's hard to think about this way because we don't usually pull things up continuously. We do a series of pulls up with our arms, like little, pull it up a little bit, stop with one arm, pull it up a little bit with another arm, and stop. But that's the idea. So you have to sort of give this extra jerk to get it moving. And then it's coming up, and you just have to apply some constant force or some constant work to keep it moving. And then when you get to the top, it's got a little bit of kinetic energy left. So you can sort of count on that little bit of motion from kinetic energy to sort of help you lift it the last little bit. Since you don't need it to keep moving, you can let it sort of coast up to a stop just a tiny bit, sort of. So that's why it takes less energy for the last part takes the least work of all three. Just a little bit of intuition you might get out of that. But anyway, that's the answer to the problem.